The 2018 Summer Institute in Migration Research Methods provided 8 days of training in the use and analysis of migration data at UC Berkeley, targeting early career scholars. The Institute drew local and national experts to train attendees and provide on-site mentorship. Most participant costs were covered thanks to an award from the Russell Sage Foundation and the Carnegie Corporation of New York.
I'm excited to be here to talk to you about causal inference today. Causal inference is a specific type of exercise that we are interested in the social sciences, which basically is about trying to identify the effect of a particular treatment or cause on some specific outcome. And so this is really trying to get at the causal effect of something in the world that we're actually interested in. And this thing could be sort of like some sort of event, some treatment, some intervention, some institution that might be changing. On any kind of outcome that we can possibly measure that would occur after the treatment is typically assigned. In causal inference, it's the specific subset we're really trying to get at the causal effect of the specific thing. Okay? And this is obviously widely applicable because in this framework you can fit a variety of kind of questions. There's various ways to think about causality, but kind of what people are in most of those areas are converging on is this idea of thinking about causality through the lens of kind of counterfactual reasoning. So the way we're going to think about causal effects, at least for this purpose, is to really think about causal effects as the difference between two potential outcomes. Okay? Two potential states of the world that can occur when a unit gets exposed to the treatment or does not get exposed to the treatment or gets exposed to some sort of control condition. The question is there's always going to be some comparison between the treatment and the control condition. And we would think that every unit that we might be able to study has two potential outcomes, which are the outcomes that we would observe for that unit under the treatment and under the control condition. Right? What would happen to a unit with treatment? What would happen to the same unit without the treatment? And the difference between those two, that's what we would think of as the causal effect for that specific unit. Okay? So this is thinking about or defining the causal effect as the difference between these two potential outcomes. That's very different than saying the causal effect is the difference between what happens before versus after the naturalization, or the difference between what happens to me and what happens to you, okay, or a third person. It's really specific to the unit that we're studying, and it's two potential states of the world that we could observe, right, with the treatment and with the control for that particular unit. If you look at this, it makes it very obvious that causal inference is fundamentally and always a problem of missing data, okay? So I guess yesterday you talked about imputation. This is also going to be imputation. We're going to have to somehow impute these question marks. We're going to have to come up with an intelligent way of imputing what would have happened to these units, right, in the absence of the treatment, or for the control units, imputing what would have happened to them with the treatment. And it's very important to recognize that this is a very fundamental problem. Okay, it's so fundamental that the technical term for this is actually the fundamental problem of causal inference. I'm not we call it fundamental because this is what we call in statistics an identification problem. It's a problem that's not going to go away even if we have unlimited data in the world. Right? So typically in statistics, problems go away if we can just increase the sample size. If we could just collect more and more data, right, we'll be able to make this problem go away. Here, this is not going to help us. Okay, if we have more units, there's just going to be more missing potential outcomes. Right? The only way to make that problem go away is to either we come up with a time machine, okay, which we haven't done yet, or we're going to have to somehow find a way to make up what this missing data is. And the way we're going to do that is we're going to have to make some what I call identification assumptions. We're going to have to impose some assumptions on the data generating process, and typically this is going to be about the assignment mechanism, the mechanism that determined, right, why units got treatment and why units got control. We're going to have to somehow put some restrictions, some assumptions on this assignment mechanism, which is then going to allow us to identify the missing potential outcomes from data that we can actually observe. And that identification assumption always is going to be there. There's just no way around it. The question is just, is the identification assumption that we make, which is ultimately the fundamental assumption on which everything that we're going to do in terms of inferring the causal effect, everything is going to rest on the validity of that identification assumption. And so if the identification assumption is going to be wrong, what we're going to make up here in terms of the missing counterfactuals is going to be wrong, and we're basically going to end up with the wrong answer. So the validity of the identification assumption is going to be very crucial. What do we have in terms of things about how we typically do causal reasoning? Okay, so obviously one approach that we often take, which might not be terrible, but often is not quite as awesome as we think, is our intuition. Okay, so often we encounter strong opinions and a lot of things like vitamin C. The problem is that intuitions can be completely wrong, right? Anecdotes. The problem is we are very biased observer of anecdotes. We typically like to tell the anecdotes of the point that we want to support. Somebody imposes an immigration policy. You see outcomes changing. It's very hard to know. Is that because of the policy, right? Or would have things changed in the same way had the policy never been implemented? Single anecdotes. It's very hard to infer causality from that. It's possible if we have a very clear and very, very large effect. So if let's say I write a book, and the book's really terrible, nobody wants to buy the book, and my book sales are really, really low. Okay, and I'm getting depressed, and then at some point I get an invitation to Oprah, and Oprah puts my book in her show, and she's like, "This is the most awesome book. You've got to read it." And tomorrow, after the show airs on Amazon, the book sales are exploding, right? And now my sales are up here. So in that case, it's seems very plausible to have this very sharp timing, right? This very big effect of this very big intervention. That my intuition that Oprah probably had a causal effect on my book sales right there. Right? I have plenty of information about the counterfactual. There was no sales 20 days ago, 10 days ago, 5 days ago, but now they're there. But most things in the social sciences aren't like that. We can look at correlations. That's obviously the next step. We want to think does A go with B, right? Do cities that are sanctuary cities is that correlated with better outcomes for immigrants, or is that correlated with higher or lower crime rates? Right? We could just line up the cities. We could see whether they're sanctuary cities or not. We could look at their crime rates, and we could try to establish a correlation. Right? The obvious problem is that the correlation in itself is not necessarily informative about causality. Right? We don't know, is it the crime rate that's creating the sanctuary city, or is it the other factors that are just different between sanctuary cities and non-sanctuary cities that might lead to differences in crime rates. Right? The third possibility, right, is what we've talked about, what was the first study was trying to do, which was basically an observational study, right, where we basically acknowledge the existence of some confounders. We try to control for those confounders somehow, and then controlling for the confounders that we can observe, we hope that the units are comparable on treatment and control. But the obvious problem with this is, right, that especially if we know that the treatment assignment is just pure self-selection, the list of the unmeasured confounders is just a bottomless pit, right? There's always going to be somebody in the audience who's going to say, what about this? Or what about this? How can you say that it's not this that is making the difference? And at some point, you're going to have to punt, right? There's only so many things that you can control for. And at some point, you're also going to run out of units, right? If you want to control for 100 different things, and you want to find people who are the same on 100 different things, you're going to need 10,000 people in your study, right? And so the fourth possibility, which is why this is the gold standard for causal inference, is we can run a randomized experiment if we can. And then we can ensure that because of the random assignment, the treatment and control group are only going to differ in terms of their treatment status and not in terms of measured or unmeasured confounders, and we can just look at the outcome difference in terms of to get it. Then the next thing you want to do is, I think through the ideal experiment. So you ask, okay, if you have unlimited resources, unlimited access to data and people, what would be the ideal experiment that you would want to run, in order to actually look at the effect? And that might be, a hypothetical study where you you could think about, okay, in the case of naturalization, it would be we take a bunch of people, we randomly assign them U.S. citizenship, right? And then we see what happens in terms of their wages. That would be the ideal study. If I really want to get an effect with naturalization. So then you're going to take a step back and say, okay, what is it that I'm actually going to be able to do, right? The ideal experiment is good to think through what is it that you actually want to get at. What's the counterfactual comparison that you want to get at, right? I want to get at the counterfactual comparison of are wages of naturalized people higher than they would be if they had not naturalized? That's the ideal quantitative interest. That's kind of the estimate of the study. But then you're going to have to think about what's an identification strategy that would actually be feasible in order to get at this. And so the identification strategy is going to be your research design where you try to find some way, right, of finding either a situation where citizenship is as good as randomly assigned, right? Or maybe it's going to be even less than that. Maybe it's just going to be comparing naturalized and non-naturalized people because that's the only thing that you have access to, trying to control for as many things as you can. So you're going to have to pick an identification strategy, and that's sometimes a lot of creativity involved in this particular step. Once you have that sorted out, you go and collect some data, and then you just do, from there on, it's just statistics. Then it becomes really easy, because then you have data, you can pick your appropriate estimator, you plug out an estimate. Obviously, you need to compute the standard errors correctly and everything, and like take your stats courses. That's important. But like the real hard work is here. Like this is really key in causal inference. Okay, if the research design is screwed up, there's no statistics in the world that can like help you fix those things. We get very worked up about statistical theory. Statistical theory is often, we can just take, for 99% of things, we can just take off-the-shelf standard results and it'll be fine. The thing where we really have to like do the hard work, where we can bring in a lot of expertise, is this identification strategy. Our research design that would allow us to rule out alternative explanations and to get a handle at these confounders. So what's the first one? The first one would be to run a randomized experiment. Okay, and I'll say a little bit more about what that is and then show an example. You might be able to do what's called a regression discontinuity design, which is kind of a quasi-experimental method. It might be that there is no quasi-experiment. At the end, you can just run sort of a difference in differences, where you're going to compare treated and control units kind of over time, using some sort of panel data or repeated cross-section. Or you might end up down here, which is what we call selection-on-Observables. I ordered these here. These are not necessarily in random order, but these are kind of ordered in terms of what would give us the highest internal validity to potentially the lowest internal validity. Okay, and I don't mean this to like beat down on observational study research. I do a lot of observational study research myself. Probably like 90% or like 80% of the research that I do has like some observational component to it. I think for you as like young researchers in this field, I do think that in the first two buckets, when it comes to migration studies, we just don't have a lot of those in migration studies in the first two buckets. So if you are able to kind of like push your research more in this direction, okay, to get higher internal validity, that's something that can be very beneficial for you if you really want to accumulate kind of causal knowledge about the things that you're interested in. So what are we doing in RCT? Well, in RCT, really the key difference to all the observational studies is that we as researchers control the treatment assignment process, right? We have the ability to randomly assign people to the intervention or the non-intervention, to the treatment and the control condition. That's really the key distinction to all the observational study designs. We, as researchers, are able to do the random assignment, or we're able to work with somebody who's able to do the random assignment. Now, what is that going to do? Well, the random assignment is going to lead to comparable groups, right? Because it's just going to depend on the coin flip whether you get to treatment and control. You're going to get two groups that are basically identical in terms of the observed and unobserved confounders, at least in expectation, meaning on average, right? If we have a very small experiment, we might end up in an imbalanced group because we got a coin flip was such that all the women end up in the treatment, all the men in the control group. There would not be a good comparison. But like, if we have a large sample size, that's going to happen with, probability 0 increasingly. So we're going to get comparable groups. Because we're going to get comparable groups, we can just look at, measure the outcomes a year, 2 years, 3 years down the line. You can just compare the outcomes between the treated and control, and the statistics are going to be very simple. Okay, you can basically do it in a coffee shop by hand. You just compare the treated and the controls. No fancy statistics needed. You compute some sort of standard errors. But another benefit of the experiment is not only it's going to give you high internal validity, but it's going to make things very simple and straightforward. It's going to be very easy to communicate it. And the other advantage is also you're going to be able to pre-register it, okay? Which some people think of a big benefit, which is ahead of time, before you actually get the results, right? You're going to say, this is the experiment I'm going to run. Here's how I'm going to collect the data. Here's how I'm going to analyze the results. And then you tie your hands behind your back. The results come back. The data comes back. You plug it in. You say whatever you did, and you go for the results. So nobody can accuse you of engaging in some sort of phishing. That can be a big benefit. That can be a big source of frustration because the most important thing that you learn is not something that you had anticipated. But then at least you surprise yourself, which is good for science. What are the downsides? I think the two major downsides is that what Irene was alluding to, which is potentially you could have very limited external validity. Okay, if the only group on which you're able to run the experiment is a subset of people that is just so different from most of the people that would typically be exposed to the intervention, then it might not be that informative. It might still be worth running it just to see what you get for that subsample, but then you want to be careful in terms of extrapolating what you find from the experiment to what you would find if the same intervention were applied to other types of people. But it could be a great starting place, and then ideally you would want to be able to replicate the study in multiple circumstances. The second one is the tough part, I think, which is sometimes it's just not going to be able, you're not going to be able to randomize for the things that you want to study. If you're interested in major policies, it's sometimes really hard to randomize major policies. People are increasingly randomizing all sorts of things, but how long did it take medical health researchers to randomize people to health insurance or no health insurance? It took a long time, but eventually somebody was able to do it. The second best alternative is typically an RDD. Okay, so how does an RDD work? Well, a lot of policies involve some sort of arbitrary thresholds, right? And so maybe a policy has like an age cut point, and you can only be, getting a particular benefit if you are above a certain age. Maybe if you have data on those units, what you can do is you can compare people who just made or just missed this age eligibility cut point. And then, right, under the assumption, and that's really key, that the units might not be able to sort very precisely around that cut point because it's hard to manipulate your birth date, then you basically get something that might be as good as a randomized experiment, which is an arbitrary assignment around this threshold of units into treatment and control. There are going to be some units that just missed and just made the cut point. Because it's kind of arbitrary, right? There's not going to be something like radically different about people who are going to have their birthday one day later than one day before. They're probably going to be very comparable in terms of things that you can observe. You can check that, run a balance check. But they're also going to be very similar in terms of unobserved characteristics. And so you're going to basically be able to compare those units at the threshold, and you're going to be able to get something that, in terms of the intervality, might get very close to randomized experiments. In fact, people have run these validation exercises where they basically randomly assign units into like 3 groups. In one group, they do a random assignment. They establish the true effect based on the randomized experiment. In the second group, they do an RDD. In the third group, they do a Selection-on-Observables, and they see, do the observational study techniques, are they able to replicate the results from the randomized experiment? And the RDD, literally across 10 different studies that have done these validation exercises in a whole variety of contexts, the RDD is pretty much the only observational study technique that consistently replicates the experimental benchmarks. The 2 downsides are, you might get very limited external validity. You're only going to get the effect at the threshold, right? And then you might not be able to find a cut point. Maybe some policy doesn't have a cut point, or there are too few units around the cut point. And then it could be very low power as well. So typically in RDD, the major downside compared to the experiments is that you just have to have way more units in order to be able to get the same statistical precision, right? Because the treatment effect is going to be identified of the units that are at the threshold only. That's going to be fewer than all the units. And so you're going to suffer in terms of statistical power. Third design, this is something that increasingly you're able to do. There's a lot of studies in that particular bucket, which I loosely call here sort of difference in differences or panel analysis. What do we do here? Well, here we basically take a treatment and a control group. The treatment group could be people who were exposed to policy. The control group could be people who are not exposed to the policy. Or it could be a group of cities or regions or schools that implemented a particular policy, and we compare those to a group of policies, schools or regions that did not implement a policy, and we basically try to follow them over time. And then what we do is we take the difference between before and after the intervention for the treated units, right, minus the before and after difference for the control units, and we basically compare the differences, right, in their post-pre trajectories. And then the idea is that if there is a differential trend, right, if the treatment group is going up while the control group remains flat, we attribute that difference to the effect of the treatment. Okay? And so the identifying assumption for this is what we would refer to as sort of the parallel trends or parallel worlds assumption, which is basically that we have to find a control group that reasonably would get at the counterfactual for the treatment group, which means that we have to assume that in the absence of the treatment, right, the treatment group would see the same trend that we saw in the control group. That's the key identifying assumption. The problem with that is that assumption, to make that assumption true, it's really very hard to do, oftentimes. It's very hard to find control units that are similar enough to the treated units that it's reasonable to think that they would follow, right, the same parallel trend in the absence of the treatment, especially if units self-select into the treatment again. In these studies, if you see a diffs and diffs, that's the first thing you want to look at. Are there some checks for parallel trends? Is there actually these days it's hard to publish a difference in difference study where you don't go through an excruciating set of checks to convince the reviewer that this parallel trends assumption is somewhat plausible, right? But it works much better in cases where the treatment is not self-selected. Okay, so the last thing I have, which is the Selection-on-Observables, is literally going to be the comparison of treated and control units, where we have not even over time data. Maybe we have some over time data, but the only thing we can do is we can just control for treatment and control. We can control for background characteristics using matching and regression. And the identification assumption here is basically either you can make a case that the control variables that you control for are the only variables that should matter, and there are no differences in unobserved characteristics, right? Or it's going to be kind of the praise scenario where you're just you're going to have to pray that there's something similar. And so Selection-on-Observables is the easiest paper to write. It's also the lowest in terms of internal validity.
Thank you for watching. Please watch the other videos in the series using the links below.